So today we will discuss material derivative and how material derivative is used to formulate Euler's equation. To understand what is the material derivative, suppose we are looking at a steady flow of an incompressible fluid through a vertical pipe. So here is a vertical pipe, and this pipe has varying cross section. Here the cross section is large, here cross section is small, here cross section is large. That means from continuity equation we should get that cross section multiplied by velocity equal to constant. Cross section is large, velocity will be small, and where cross section is small, velocity will be large. So in contrast, think about a uniform pipe where there is no variation in the cross section. Then when water falls from top to bottom, it just is influenced by the gravity. So that means if the initial velocity is say u, after time t, the velocity will be u plus gt, where g is the acceleration due to gravity. So there, in the simple case, the velocity will be simply a function of time. But here, due to the shape of the pipe, we see that of course there is a variation with respect to time, whereas variation of velocity with respect to time, but also there is a variation depending on its space coordinate, that is the z coordinate. So this is what we will be interested in, and we will see how to tackle this situation where velocity depends on the location where we are looking at. So here the velocity, we can say velocity is not only a function of time but also a function of space coordinate zt. So we can say it is a field, it's a vector field. It is a function of two variables, time as well as the z coordinate. I want to take the derivative, the rate of change of velocity, then this requires a derivative that accounts for both time variation as well as spatial dependence along the particle's path. So this is the main reason why we have to consider the material derivative, because we have to formulate a derivative that accounts for both time variation and spatial variation along the particle's path. If we take the total derivative, then we can apply chain rule. First of all, it is a del v del t term, and then there is a del v del z term, but del z is again a function of t, so chain rule gives del v del z dz dt. But dz dt, this is the velocity, so we get the total derivative dv dt is equal to del v del t plus v del v del z. So that is the difference. Now the operator is del del t plus v del del z. And in 3 dimensions, it will be x, y, z and t. So velocity will be a function of 4 variables x, y, z and t. That means if we want the total derivative of v, so first of all there will be a del v del t term, then there will be 3 terms because of x, y, z. First del v del x in dx dt, then del v del y into dy dt, then del v del z into dz dt. But these are the components of velocities, vx, vy, vz. So these 3 terms here together, they give v dot grad operating on v. So this operator is the derivative which takes into account both the time variation as well as the space variation. So next is the pressure force on a fluid element. Let us consider a fluid element. Now the pressure force acts on the surface because it's a surface force. So if we look at the element, then on the left side and the right hand, the left side of the element and right side of the element, we can just use the Taylor expansion. So px plus dx by 2 del p del x. Here, from here, if we take Taylor expansion, and x minus dx by 2, px minus dx by 2 del p del x. Now if we subtract, which acts on the element, there is a minus sign, and then dx into del p del x. And from pressure, we want to get force, so we have to multiply with area. So area is nothing but dy dz here. So that means dx dy dz, all three things come. That means the force becomes minus del p del x dv. And similarly, we have to take y and z, which will give del p del y dv and del p del z dv, all with minus signs. So that means if we add them vectorically, then I fx plus j fy plus k fz gives the force vector. It becomes minus gradient of p dv. So this is our pressure force on the fluid element. Next, we need the body force. The body force is the given by if we take the small element, then the mass is rho dp, and small body force is mass into acceleration, that is rho dvg. Rho dvg is the small body force on the liquid element. And lastly, let us look at the acceleration, because this is, we have already seen, this is the material derivative, which is the acceleration, and if we multiply acceleration with mass, then we will get force. So then we have to balance using Newton's law. Newton's law gives this force, mass into acceleration here, and here we have the pressure force and we have the body force. So if we balance all three, then this is the equation, dv will get cancelled. So rho multiplied by this material derivative of velocity is equal to minus gradient of p plus rho g. So this is the Euler's equation. So in conclusion, continuity implies special variation of velocity in a flowing liquid. The material derivative captures the true acceleration of a moving fluid particle, because the velocity has the dependence of time as well as dependence on the space coordinate. So the material derivative is needed. Pressure gradients and body forces together determine fluid motion, and Euler's equation provides a unified description of fluid dynamics. So I hope that you have found this talk interesting, and thank you for watching.